Hello, can you hear me? Can you hear me now? Great. Okay. So, 61C, great ideas in computer architecture. So today we're going to keep going with our introduction to the C language. So I'm going to sort of rewind a little and recap stuff we did at the end of the last lecture. So first of all, components of a computer. So we have the processor over here on the left-hand side. That actually does the brains, does the work, does the arithmetic operations, makes the decisions. On the right, we have, in the middle here, we have the memory. This is where all the data is stored, where the program is stored in your computer. So the processor is fetching instructions from memory, it's fetching data to work on and putting it back into the memory. Then we have I/O. So memory is just a whole bunch of bytes, just a whole bunch of cells. Each cell stores 8 bits in most computers today, so 8-bit bytes, and that's where all your program lives, all your data lives. So, going to the C language, I want to make this distinction between an address and a value. So, an address is just the number you give each cell to tell you where it is. So this is, address number 5,943, and there'll be a byte stored in there. There'll be, billions and billions of these bytes in a modern machine, modern laptop. So the addresses we talked about last time, typically these days, they're just unsigned numbers. So the address itself is just a number. So the machine can manipulate addresses. They're just more binary numbers, okay? And so it's very important in thinking about when you're programming in C, dealing with pointers, or just dealing with machines, as you look at the instruction sets later on as we go down the assembly level, don't confuse addresses with values, right? Address is where something is. The value is what's stored in that cell. Okay, so in this example, these cells are numbered 101, 102, and so on, and inside each cell there's some value stored. So a pointer in C is a variable that contains an address, right? So it's just another number. A pointer is just another number, but it's being interpreted as the location of some other cell, right, some other variable. Okay, so it's a number that's being interpreted as the address of another variable. So just to make that concrete, here's a row of storage cells, and the variable x. The compiler figures out, okay, x is stored in location 104. I'm going to put it there. Next time we'll talk about actually how the memory is allocated. But for now, just somehow the compiler magically associates that symbol x with location 104 in the memory. And the current value of that cell is 23. So right now x, if you were to print out the value of x, it would have the value 23. The way the computer would work, it would say, x, I know that's at location 104. Let me get the value from location 104. And what is it? Oh, it's a bunch of bits representing 23. Right? That's the value of that location. So we're also showing y. That's a different variable stored somewhere else in the memory as a value 42. So pointer is just another variable. So it's another location somewhere in memory holding a number. But this number is interpreted as the location of a different cell, okay? So, P can point to another cell. That's why we call it a pointer. It points somewhere else, right? And so in this case, if P was pointing at X, the value stored in P's storage cell would be 104, because that's the address of X. Question?
How do you distinguish between like a number that is supposed to be like an address and a pointer as opposed to like a regular
So the question here, good question. How do you distinguish between a number being used as an address to point to something else, or a number that's being used as just an integer value? Well, the reality is at the machine level, the machine doesn't know. They're just a bunch of bits. The memory just knows it's a bunch of bits. It just stores the bits. It doesn't care whether they're pointers or values. The processor, different instructions, we'll get to that later, understand that, in this context, I'm using it as an address, and I will then use it to I'll send this bit pattern over to the memory as an address. Other instructions will read the values from a cell and use them as an arithmetic operand in an add. And so the context will tell you how to interpret those bits. The memory is just a bunch of bits, right? It doesn't know. It's just ones and zeros. It's how you interpret them that decides whether they're pointers or values, arithmetic values. Hopefully as we go through this, you'll see how at the C language level, the code you write will distinguish your use of it as a pointer or as an arithmetic variable. So the syntax, how you declare a variable to be a pointer is, so you kind of write it out as what type of value you want it to hold. So the first example here is an int, a pointer to an int. So it's int x, but with a star. So this means pointer to an int. So int star x says this variable x is the address of an integer somewhere in memory. So during the execution of your program, this variable cell x will always be interpreted as holding an address because you declared that this is the type of this cell. This is a pointer cell, right, x. To actually get an address into x, you have to assign it something, and you have to assign it addresses. So the only legal things, now that you've declared that x is a pointer variable, the only legal things you should put in there are addresses, and specifically addresses of integers, right? You've declared its type to be, I'm a pointer to integers, so the only values x should have are addresses of integers. And the way you get an address of an integer is using this, or of anything, is using this ampersand operator. And that means get the address of. So when you say x equals ampersand y, what you're saying is assign to storage cell x the address of variable y. That's very different from saying x equals y without the ampersand. That would say assign the value of y to x. X equals ampersand y means assign the address where y is stored to x. Okay? And the compiler will check if you do the wrong thing, you'll get, a type error. If you try and say you were to say x equals y, the compiler would say, warning error, you're trying to put a value into a pointer, and that'll mess things up later. The second thing you can do is dereference a pointer. If you have a pointer, how do you use it? Well, you dereference it. So you say, in this last example, z equals star x. That means to the compiler, take x, treat it as an address because it is an address. The star means dereference it. So instead of getting the value of x, treat x as an address, go to memory, and get to the thing stored at the location given by the value of x. Is that a question? That's right. So z, in this case, z would have to have which type? Int, right? So you're assigning to z something pointed to by x. The type of x is a pointer to integers. So it has to be that when you dereference x, you're going to get an integer. And so whatever you assign that value to has to be capable of holding an integer. So z has to be given the type int. So somewhere previously you would have declared that z is an int variable. Okay? So we're going over this. So ampersand operator gets the address of a variable. Let's just go through this schematically. So here's two storage cells in your machine, P and X. One's a pointer, one's just a plain integer. You can declare these all in line. You can say int star P, comma X. That just saves you repeating the int. You could say int star P, semicolon, int X, semicolon, but you can just say int and then declare a whole bunch of things that are all ints on one line with commas in between. Okay, so you have P and X as two storage cells. One is a pointer to int, one is an int. You can just assign to x equals 3. Right? 3 is an integer. You can put an integer in x. That's fine. Now you can say, well, I want P to point to x. So I say P equals the address of x. And usually when you do these diagrams or you're drawing on the whiteboard, you'll show a pointer as an arrow going to a cell. That's a standard way of representing this when you're talking to people about what's going on or illustrating it. Now if you want to dereference it, you just use that star operator. And so, for example, remember there's this print formatted command in C, printf, that takes a string that says what you want to appear. Within that string, there are special % characters that indicate replace this point in the string with something from the argument list following the string. So %d means print an integer here. And so the string p points to %d, and the argument is star p. That means dereference the pointer p. P is a pointer to an int, so star p is the integer that it points to, and so then this will print the value of 3 on the screen. So one thing to note here, the star here is used both to declare the type of the pointer when you say int star p. It's also used as an operator when you say star p to dereference the pointer. Okay, so it's used, the star is used in two places, and depending on the context, you can tell which is which. Question?
Does the pointer variable always have to be of integer type? So
So good question. The question was, does the pointer always have to be of integer type because it's always storing a pointer? Well, the answer is no. In fact, the type of the pointer is always pointer to whatever it points to. So pointer to int is actually its type. Now, under the hood, inside the machine, it turns out on all modern machines, all pointers are just, an unsigned integer, right? But to make sure your programs, help you debug your program, get them working in the first place, you put the type on to help you ensure you don't assign the wrong thing to it. You could just have unsigned int. You can imagine a language where you didn't have these types. And in fact, BCPL was like that, the predecessor to C's predecessor, right? So everything was just a word, right? And they could be pointers. It was really hard to debug because you would get confused. Here the compiler will tell you, because you've declared this cell should only hold pointers to integers, even though under the hood it is just an integer address. The compiler will type check and make sure you don't try and do the wrong thing with it. Good question. Okay, so we've seen how to use the pointer to read, to dereference it. Oh, sorry, question at the back. So the question is, what happens if you do p equals x? Anybody want to answer? Louder. Error, yeah, because x is an integer, p is a pointer to an integer. Those are two incompatible types, right? So the compiler will say, whoops, you're doing something wrong here, right? Now, it turns out in C is designed for a very low-level programming. You can subvert all that checking and tell the compiler, I actually mean to do that, but we won't cover that for now. That's a way of introducing lots of bugs. For now, rely on the type system and the compiler to help you do the right thing. So if you say p equals x, it will say, sorry, x is an integer, p is a pointer to an integer. Those are two different things. You cannot assign an apple to an orange. It's a different kind of beast. So using the pointer for writes, so star p can appear on the right-hand side of assignment. It can also appear on the left-hand side. And that means, say you got this scenario again. If I say star p equals 5, that means change the cell that p points to hold 5, right? So p is pointing to some cell. Star p equals something means use that address, locate the cell it points to, and in that location that's pointed to, write the value on the right-hand side of the equals, right? So then this would result in x being assigned 5. Okay, so p doesn't change. The thing p points to is changed in this case, okay? So that's assignment dereferencing a pointer on the left-hand side of an assignment statement, okay? So we can use pointers to help with parameter passing. So by default in Java and C, always, the parameters to a function are passed by copying their values. And so you get a copy of every value in each argument, not the original version of it. So this is made clear by this little example. So I had a function called add1, and my intent was to write a function that increases the value of its argument by 1. Notice this doesn't return anything. It just updates x and adds 1 to x. However, this doesn't really work as intended because when you call this function, a copy is made of the argument. So you call it with some value, 3, say. Or in this case, y. So I'll assign 3 to y. I'll say add 1 to y. And it doesn't really add 1 to y. What happens is at the call site, where you say add 1 y, the value of y is read, it's 3. 3 is then passed to the invocation of add 1. So internal to add 1, it'll see 3 come in. X will be assigned the value 3. Internally, you'll say x equals x plus 1, so x equals 4. But nothing's returned, and that value of x disappears once add 1 returns. So nothing actually changes in your program, right? You just create a local version of x, incremented it, and it disappeared when you returned from add 1, right? So y is still equal to 3, right? You just copied from y to write to the argument that you then call this function with. So if you actually want to call a function to change some variable, you have to pass a pointer to that variable, right? Because the pointer can be passed by value, but then you can indirect through that pointer to actually change the original storage cell, actually change that value. So see that here. So now we want to add 1, and instead now we have an int star as the argument, an integer pointer. So p points to a cell, and inside add 1 we say star p equals star p plus 1. So read the old value that p points to some cell, read its value, add 1 to it. Now write that new value back to the location that p points to. So notice here, p isn't being changed by this function, but the thing p points to is being changed, right? So now you get to mutate the value in memory. So now int y equals 3, add 1 to the address of y. Now notice here, y is an integer, int y equals 3, it's just an integer. And so when you call add 1, you have to use that address operator to get it to the right type, to extract the address of y. Because what you're passing into that function is a pointer to an integer. Y is an integer, address of y is the pointer to that integer. Is there a question up there? No? Okay. Yep. So the question is, if the variable was already an address of something, do you need the ampersand? No. If it's already the right type, for example, say you had another pointer q, and it was already a pointer, you could just pass q directly in. You just need the address of operator to find the address, take a variable in memory, and convert it to the address of that variable in memory. That's what ampersand does. If it's already a pointer, you're fine. Right? The value of that pointer will be copied in, and it would just increment whatever it was pointed to. Yep, question?
What would happen if it wasn't pointing to anything when you passed it?
Great question. So what would happen if it wasn't pointing to anything? We'll actually talk about that in a couple of slides, and the answer is bad things, right? Bad things happen. If you're lucky, your program crashes. If you're unlucky, something you didn't know about got changed behind your back in a weird way that you'll never uncover, right? All right. Okay, so that example now, once you've added 1 to that y now, it does become equal to 4. Okay? So you can create a pointer to any type of object. So as I mentioned before in answer to that question, the type of a pointer is actually changed depending on what it points to. And this is to catch bugs where you're trying to do the wrong thing with the wrong kind of variable. Right? But you can have a pointer. You can create pointers to anything, to integers, characters, a whole struct. You can even create a pointer to another pointer. And I'll talk about that a bit later. Now normally, it just points to one type. There is a special sort of exit case, escape case in C called void star. So a void star is a pointer that can point to anything. Like, it's like the Joker. It can just point to anything, right? The pack of cards. And you need that to get around some limitations of C. The trouble is, because the compiler will let you treat it as a pointer to anything, it won't check for mistakes for you. And so if you try and you might just do something bad, incorrect, and the compiler won't have any way of telling you were wrong, right? So you have to be very careful when using it. It's a great source of bugs, security issues, other bad things, right? Just using void stars everywhere. You might get lazy and say, well, I don't want to figure out what type it should be. I'll just make it a void star and just fill my code with void stars everywhere. It'll be impossible to debug your code. It'll also be lousy code to read, right? Because the main reason of putting all this stuff in your code is not for the computer. It's for other humans who have to read your code, right? It's very rare you get to write a program from scratch. Most of the time you're modifying somebody else's code. And it's great to be able to read their intent. You can capture some of that intent from the types they've assigned to all their variables, right, as well as the variable names. Okay, so getting at what happens if it doesn't point to anything. So when you declare a pointer, all you're declaring is, I need some space in memory to hold a cell that's going to hold the address of something else. You don't actually create the something else, right? Because what it points to can change over time. That's kind of the whole point of having a pointer, right? You can change at runtime what it points to. So when you declare a pointer, you haven't necessarily declared anything that it points to. And so this little example, I declare a pointer, PTR, pointer, int star pointer, points to an integer. And then I assign to whatever it points to, star pointer equals 5. So what does pointer point to? What is it pointing to? One answer here was null. If you're lucky, it might point to null. But the C standard says any local variable inside a function that you don't explicitly initialize is undefined. I don't know, it could be anything, right? So it's bound to be the worst possible thing for you. That's Murphy's law, right? So star pointer probably points somewhere that you won't really find until 3 weeks after debugging it for endlessly, right? That it overwrote something somewhere else in your program that you cared about, right? So the point is that when you declare int star pointer, there's no value placed in the pointer cell itself. It's whatever was in those bits in memory before. That's the way the C standard is defined, right? So there's just garbage in pointer. And if you then try and assign through that pointer, the compiler doesn't really help you here. It just says, okay, pointer is a pointer to integer, and you're assigning an integer to it. That's fine. I'll read the value in pointer. It seems like an address. I will then write to that cell and put 5 there. Now, the compiler, they are better these days. They'll give you warnings about, maybe you didn't actually initialize this. You may want to think about initializing it, and you will get warnings, but not in all cases. Yep. Right. So, so this is a function. We'll talk more about how memory is allocated next time, but this is just a function, and those variables you declare within a function only exist for the lifetime of this function. So when you exit f and return back, pointer disappears. However, the damage you've done, as you say, I've dereferenced pointer, and somewhere else in memory, there's some place I've corrupted with the value 5. So sometime later, you're going to find 5 in some storage setting. But where did that come from? Right? Where did this 5 come from? And it'll be this stray write from this uninitialized pointer is the problem. Okay. Question?
Yeah, what if you try to assign an integer to the address of a pointer? Would that just self-destruct?
So the question was, what if I try and assign 5 to the pointer directly? To the value?
The address, yeah.
Yeah, well, this gets back to the type argument. So that one the compiler can catch, because it can say, oh, that's an integer. You're trying to assign to a pointer to an integer. Those are two different things. So it will then say, type error, wrong kind of type. That's a question?
So how would you avoid this? How would you fix it?
How would you avoid this? So one thing is, when you use C compilers, they have different levels of error reporting. And if you're a good programmer, you will write extremely clean code that even on the highest level of error reporting, there's no warnings. So sometimes, because it's not sure if it's actually an error, it will just give you a warning saying, I think you may need to initialize this variable. On GCC, it's $W all. The dash W is the option for warnings. And the option all, it reads like dash wall, dash big W, little all. That says, tell me every single possible thing you think I'm doing that might be possibly wrong. That's one way of helping catch cases like this. Unfortunately, C is a low-level language, and sometimes you get these infuriating errors that are really hard to catch. But write clean code, put types on everything, don't use void star, look at the compiler warnings, be scrupulously clean in your type declarations, and look at all the warnings the compiler gives you. It's trying to tell you, to help you out. So that's the way to reduce the pain you're going to get from programming this low level. Sorry, can you raise your hand? I can't see. Sorry, okay. Okay, so wall is pretty much everything. There's probably, if you go read the GCC man page, you'll find out even more exotic things. But generally, use the compiler to find the bugs for you. Don't try and find them manually. And don't get lazy in writing your code, because that's actually false economy. You spend a long time debugging if you don't do the right thing. Okay, let's talk about pointers and structures now. Okay, question?
Clarification. So the pointer in the previous slide was just pointing to garbage to begin with, right?
Right, so when you declare int star pointer, you haven't assigned it any value, so it's just garbage, yeah.
And so when we're assigning it to 5,
Yeah, so go back to that first picture I showed. Memory is just a big lump of bytes, right? And every byte has a number. Right, so when you declare int star pointer, it's going to have some value in there, 5,342,000, whatever. And when you say star pointer equals 5, that cell somewhere in memory is going to get overwritten with 5. Now, as a programmer, you think that cell is holding my variable b, right? So I have a b variable somewhere else in my program. And when you read b, you're going to be, where did 5 come from? And because B is just a storage cell in memory with some address, when I write to through some stray pointer, I may update that other thing that, it's actually some variable B. The compiler put this other value over there. And because you had an initialized value in P, in the pointer, you overwrote this other variable, right? That's the way it appears to you in the code. All of a sudden, my variable had never assigned that value to that variable. How did that happen? And what happened was it was through a pointer, you had the address of that variable, and you overwrote it accidentally. Okay, so pointers and structures. So remember, we can declare structures in C, which are combinations of variables that form a coherent record. So one example here is you want to represent a point in an XY space. So you declare a struct that has two members, X and Y, two integers, X and Y. And then what I'm showing here is, once I do this typedef struct index in Y as a point, I can then declare instances of that struct. So P1 and P2 are two different points. And each point has those members, P1.x, P1.y. Just like in Java, you dot through to get the member fields out of that structure, right? Now, one thing you can do in C, the long way of using a pointer to a struct is to, so one thing to say is here, I can declare a pointer to the struct just by saying point star P address. So as you might expect, this says P address is a pointer to a point struct, okay? So it's a pointer to a point. I can dereference it by doing star P address, and this dereferences it and makes it a struct. Then I can just dot into that, okay? That's one way of dereferencing it using a pointer, dereferencing a pointer to access a struct. There is another syntax in C, which is, because this is so common, there's kind of a nice shorthand, which is to use an arrow. So you can just say point P address arrow, which is a hyphen and an angle bracket, X. And that means get me the member field X of the struct that P points to, the pointer points to, all right? So these two are the same thing, just written differently. These are equivalent. But, C programmers tend to use this form because it's kind of nice and it's kind of graphic. It shows you, follow the pointer to the X member of that struct. Okay. One other thing I should mention while we're doing structures, you can do, C supports what we call structure assignment. So instead of just copying each, say you want to copy point 1 into point 2, you could do, P2.x equals P1.x and P2.y equals P1.y. But you can just say, P2 equals P1. And in C, that copies all the members over the other struct. What it doesn't do is what we call a deep copy. It won't copy anything that it points to. It just copies the actual values stored in the struct here, right? So if there was a pointer in that struct, it wouldn't sort of follow the pointer and go copy that as well. It would just copy the actual things in the actual struct itself, right? So that's a structure assignment. Okay, so looking at pointers, they're very powerful, but double-edged sword, they're also very dangerous. So why do you use pointers in C versus not using pointers? Well, the great thing is if you want to pass a large object around, something that takes some megabytes of memory, and you want to call a function on it, instead of copying the whole thing and calling by value, you can just pass a pointer to it. So instead of copying a megabyte, you can copy a few bytes of pointer and pass that as an argument into the function. Also, as we saw, if you want to actually modify the object in the function, you want to pass a pointer to it. And like we keep telling you, this is the biggest single source of bugs in using C, so be very careful every time you deal with them. And it comes worse when we deal with dynamic memory management, which we'll do in Thursday's lecture. So why are pointers in C? Well, there's a few reasons. One, at the time the language was invented, compilers weren't that great. And computers were so slow, 25,000 times faster, probably even more than 100,000 times slower than they are now. And C was really designed to let the programmer say exactly how they want the code to execute on the machine, but still being above machine code, right? So it's portable, it's sort of barely portable, just above the assembly level. Now today, a lot of applications, you can code a lot of applications and get reasonable, acceptable performance without using C, without using pointers, right? So you can use Java, you can use Python. For a lot of applications, you don't need utmost performance. And if you don't, you should use one of those other languages because you'll avoid all this low-level, hacking and bugs and so on. But as you saw from the survey last time, it's still a very popular language for writing applications, partly because it does give you very high performance if you use it right. And also, the original reason it was invented was as a low-level systems programming language where you actually need that low-level access. I actually need to know about addresses. I need to fiddle with bits in the machine. And at that level, C is just the standard thing everybody uses. And that's why C is popular. You can do that very low-level hacking. You can get very high performance when you need it, even though it can be painful sometimes to debug C programs. Okay, so I've done a lot of talking. Your turn to do some thinking, I hope. So it's clicker time. All right. So I'm going to go this little example, this little quiz. So I want you to at least try this at first by yourself without talking to your peers. Just do your own sanity check. Am I following what's going on here? So there's a little program here. Little function takes two arguments, 2-pointer arguments, right? Does this bit of computation with it. I set up some variables, then I call the function 3 times, then I print the result. And these are the 5 cases. What does this print when it's done? Okay? So I'll give you sort of 2 minutes just to pause this, make up your mind. Yep. AA. The frequency code for clickers is AA. Oh. It says it's on. Is anybody's clicker working? People get 61C? Nope. Okay, let me try resetting this guy. That would be part of the problem. What's it called? Oh, I know. Okay, yeah, it's going now. Sorry about that. It shows you the distribution. Let's give it another 30 seconds or so.
Everybody else is seeing it, so maybe
try powering on and off. I know.
AA.
See, on AA, the frequency code is AA. just the default. Anybody else having trouble with their clicker? Okay. All right, let me... Okay, let's just stop there. All right. So, let's see how everyone voted. Okay. Most people picked B, but there's a bunch of people who didn't. Okay. So I'll give you another minute or two to chat amongst yourselves and try and convince each other what the right answer is. I don't know.
Oh, okay. Operator mode. Oh, okay.
Switch over to the B2 right now.
Okay.
I think that'll work better. The top projector is really weird.
Okay, let's stop there. Okay, and okay. I guess your peers convinced you. Yeah, that's good because that is the right answer. So let's just step through this. So this function is actually something you might have in the middle of a sorting routine. And what this does is it compares the values you're pointing at, and if one's bigger than the other, this is just a copy, right? So it just swaps the values in x and y. If x is greater than y, it swaps the two values. So if a is greater than b, it swaps it, so you get 3 here and 2 there. B is greater than c, you'll get 3 here and 1 here, and then finally this will sort these two. So you end up with 1, 2, 3 sorted in the reverse order, okay? So there you go, a little piece of pointer code. Okay, let's stop this guy. There we go. All right. Okay, let's keep going. A bit of a minute trivia. So anybody who's waiting, concurrent enrollment, anybody on the wait list, we can accommodate everybody, but you have to enroll in a lab or section that has space, right? So if you want to guarantee you get enroll in one of the other labs, then later try and move, right? So first enroll in a lab or a section, and then move yourself later, right? That's the way, if you're stuck on the wait list right now, that's probably why. Right, we should have space for everybody. Homework 0, the rest of it's all due just before midnight, Super Bowl night. So after the party, just, finish your homework. Probably better to do it before the party and turn in early. One other small change on the schedule. So midterm 2, we moved it back just to accommodate scheduling the subjects. It's just on the Thursday of the same week. So it's now on Thursday, April 9th in class. Okay, midterm 2. I think that's all we have in terms of Ministrivia. Any questions about the course organization or things that are going on? Yep. Sorry, I can't hear you. How do you turn in the homework? You should follow the instructions. Part of the homework is reading the instructions on how to turn it in. Okay, any other questions? Sorry? The first part was due in your lab section, and the last part, whichever lab you're in, you're supposed to turn in the lab, and the last part is due on Sunday. Okay. All right. Let's keep going. So arrays. So we've talked about pointers. Another feature of C is arrays. So we've already talked about structs, which are one way of grouping together a bunch of variables into some logical entity you can manipulate in the program. Arrays are a different kind of way of grouping things together, just as a mathematically indexable array. So in C, you can declare an integer array in this syntax. So you have, this is the type of the elements in the array. This is the name you want to give to that array. And then in square brackets, you give the number of elements you want in that array. So that declares an array with 2 elements. And in C, the arrays start at 0, right? So the first element is index 0 up through, in this case, 0 and 1 would be the 2 elements in this array, okay? You can also, at the point you declare it, you can actually initialize it straight away using this syntax. So within curly braces, you just give a list of the initial values of the elements of that array. So int array, and notice I don't have to give the size here because it's implicit in how many elements I give in the initializer, right? So this initializes a 2-element array, and the 2 elements are given the respective values inside the braces, okay? So strings are another common thing you want to deal with in programs. So strings in C are really just an array of characters. And so you can declare them like this. So char is short for character, and that's the C name for the an element within a string. So I can just give it a name string. And then I can use double quotes around some text. And that double quotes is a way of initializing that string array. So double quotes means this is a string literal, like the string I'm just giving you in the program text. So make sure that this variable string has enough space to store those 3 characters in the string, A, B, C. So in C, those would be 3 bytes. A, B, C would occupy a byte each. In C, strings are, the way you know how long a string is you have to read it to the end and find a 0. So they're null terminated. So as well as A, B, C in the string, there'll be another character, another byte, which stores a 0. And that's the way you know you've got to the end of the string. So in C, you don't know the length of a string until you've read to the end of it. Okay, yep, question?
You just said it was like 1 byte, but I thought that each number letter had like a byte representation, like let's say or there was like A was like 50, you know what I mean, like B was 51.
Yeah, okay, so the string, the question was about how this is represented inside the memory of the machine. So the string ABC, the A will be stored in a byte, and that byte, so there'll be a space allocated for that byte in memory, and that space will hold a number representing the code for A. So there'll be an 8-bit number that represents the code for A. Next to that will be another byte of memory that have the 8-bit code represents B, another 8-bit code for C, and then finally there'll be another 8-bit cell that holds a 0 that says that's the end of the array. So an increasing memory address. So, 1 byte is A, 1 byte is B, 1 byte is C, and the last byte is 0. And that's a string in C. Okay, that's the convention in C. So you don't know the length ahead of time. You have to actually walk down the string to find how long it is. And you better hope somebody put the 0 there, right? You just keep going. So this little loop here is one way of calculating the length of a string. So how long is a string? Well, if I pass in the string here, so notice I'm declaring the type of this argument as being a character array, and S is the name of that character array, and I set the index to 0. While this element of this array is not equal to 0, increment the count and keep going. So now this is stepping down the array, looking for a 0. When it finds a 0, it knows it's got to the end of the string and can then return n as the length of that string. So this is a standard library function in C. What's the length of a string? Strlen. Okay? Now, one key thing about C is that arrays, array names, the name of an array, and pointers are kind of in this weird duality where they're almost the same thing. So when you declare an array variable, it's almost identical to a pointer. So you could have declared that string instead, saying char star string instead of char string with braces. And it's nearly identical. There's some subtle differences, but basically that name string, when you make an array declaration, the name by itself is effectively a pointer to the first element in the array. Right? It can behave just like a pointer to the first element of an array. If our AR is an array variable, it looks like a pointer. So AR0, using the array syntax, AR square bracket 0, to read the 0th element, is the same as doing star AR, right? Because AR is also a pointer. It's the name of the array. It points to the beginning of the array, but it can be used as a pointer. So you can say star AR and get the first element of that array. You can also add to a pointer, and we'll talk about that in the next few slides. So AR plus 2, remember AR is, pointers have a number that represents the address in memory. You can add to that number. So if I have a pointer somewhere, I can add 2, and that's kind of 2 cells over. So AR points to the base of the array. I add 2 to it. I point to 2 elements into the array, and then I can dereference that expression, right? So I do a star on the sum of AR plus 2, and that extracts the second element, actually the third element of the array, 0, 1, 2. So it's the third element is being extracted there. We'll talk about point arithmetic in a minute. But first, I want to talk about what if I want to write functions that change pointers? Right? We talked previously about writing functions that changed regular variables like integers. What if I want to write a function that changes a pointer? So here's a little example of how not to do it. Right? So I write a function that increments a pointer. So I pass it a pointer. I add 1 to it. So what happens? Right, here's my little example. I create an array with 3 elements, 50, 60, 70. I then initialize the pointer q to equal a. Notice what's going on here. So I've declared an array. A is the name of the array. A has type of pointer to int. It points to the first element of the array. Because this is an integer array, A has the type pointer to int. And so I can assign it to q, which is a pointer to an int. So now q points to the start of A. I then call a function with the value of q. Then here I print out what does q point to when it's done. Right? So we start off with A pointing to the base of the array. Q gets assigned to the same value. I then call this function, which is supposed to increment it. But what happens when I print it? It's still the same value, right? So what I print out is 50, right? So q initially pointed to 50. I call the function to increment q, but lo and behold, it hasn't moved. It's still pointing at 50. So what happened? Why didn't p move along in that increment pointer function? Yep.
Because you pass a pointer by value.
Right, so the answer is, well, I pass the pointer by value. So, as in any call, all the arguments, you copy the value of the arguments at the place of the call into the invocation here. So I copy the value of Q, then I call this function. All the function did was increment its local copy, which is named P inside there, and then when it returned, P had disappeared, and Q was where it was before. So in order to change the value of a pointer, I have to pass a pointer to the pointer, right? I have to point at the pointer so I can change it, right? And how do you declare a pointer to a pointer? You just add another asterisk, right? Right? So a pointer to a pointer is just int star star, right? So this is, notice this function declaration, the increment pointer now, int star star h is a pointer to an integer. And you can nest this ad infinitum. You can have star 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 h as a pointer to a pointer to a pointer to a pointer to a pointer to, and so on, right? So what happens in this code now, notice I have star h equals star h plus 1. So this increments the thing that h points to. And what does h point to? It points to a pointer, right? So the pointer is going to get incremented. So I declare an array with 3 elements as before. I assign Q to the start of the array as before. Now I call increment pointer. And an important thing here is I take the address of the pointer, right? Because I want to know where that pointer lives in memory. So I need a pointer to the pointer. How I get a pointer to a pointer is get the pointer and take its address, right? That tells me where the pointer lives in memory, right? So the ampersand gives me the address of the pointer. I then pass that address into this function. This function then uses that pointer to the pointer to change the pointer, right? And then returns, and lo and behold, now Q will point to 60, and when I run the print, I'll get 60, right? Question? The question was, could you point pointers at each other? Good question. So what do people think? One question you have to ask yourself is, what type would the pointer have to have such that a pointer could point to something else that was pointing at it? Void star, right. So if you have void star, for sure. Because void star is like, I don't know what type it is, you can point to anything. So I can point to you, you can point to me, it's all good. But, if you actually think about it, a pointer to an int, if I want to point at that, I need a pointer to an int. But if he wants to point at me, he's going to have to be a pointer to a pointer to a pointer to an int, and so on, right? And so you run out of... So unless you use a void star, the types won't make it possible, right? So any way you can point at each other, if you both agree not to, we'll just call each other void star. I know what you are, right? Good question. So as you probably guessed, C arrays are very primitive. So they're really just a chunk of elements in memory, a block of memory, where you declare sort of where the beginning is and how many of them there are and what type it is. And a C array doesn't, notice all there is about the array is where it begins in memory. I don't record how long it is even. So it's very easy in C to declare an array a certain size and go indexing off the end. And it has basically the same effect as a stray write through a pointer, right? So I can declare an array to have 100 elements and then write to the 2000th element. What does that do? Causes havoc somewhere else in memory, right? I just updated something I didn't know about. In most cases, you have to sort of pass the array, the name of the array, along with something telling you how long it is, right? It's not encoded for you by default. You might ask, well, that seems strange. Why would you do that? And the answer is that you can build custom data structures that are very efficient, but require a lot more work on your part to make it sure they're bug-free, right? So it's very common in C to get what we call segmentation faults and bus errors. This means, these are the good cases. When you get a seg fault or bus error, this means you did something so wrong the machine knew it was wrong and stopped and reported it to you, right? The bad case, your program keeps running and does really weird things, right? So in class, we'll teach you about debugging aids that will help you debug your programs to find the errors you're undoubtedly going to have in there, right? So this is one little tip. So when you're playing with code and you want to one standard thing to do is when you have some magic number in your code, like 10, what does 10 really mean? Instead of writing 10 everywhere, because you know that's the size of something in your application, you should define it with a constant, then use that constant name everywhere else. So instead of just having, for this example, I declare array to be size 10, then by looping through it, I use 10, the literal here again. Instead, declare a constant. Const int is the syntax. So this part is the same as any int declaration, but then you just add const in front that says this is just, I can't change this at runtime. Then you can use this array size everywhere. And so then, if logically in your program you say, oh, it shouldn't have been 10, it should have been 13, I can change it in one place. Instead, I'm defined all the instances of 10 in my code that were supposed to be that 10 and change it to be 13, right? And this is a very general programming principle of, it's called dry. Don't repeat yourself. So, you're trying to figure out all the places in your code where you're sort of writing the same thing over and over again. And there's usually some way in the programming language to package those all up into one place and then just use a symbol that points back to the one place where something is defined. In this case, the size of this array. All right, so use defined constants. Question? Are arrays in C mutable? Yes, very much so. So by default, they're just variables in memory. As we saw, you can index into them and assign to them. So a square brackets 3 equals 12 would be an example of just changing that element.
Yeah, I mean, in terms of size.
Oh, can you change the size of them? Not really. Next time we'll talk about dynamic memory allocation and how you get different sized objects. So I'll defer that till next time. We'll talk about that next time. So the question was, how do I allocate arrays that change in size at runtime? So one detail I've kind of glossed over so far, but is actually quite important, is C lets you declare objects that are different sizes, right? So the smallest object is a character, a single byte, but you can have an integer which on a lot of machines is 4 bytes or maybe 8 bytes, or a long, which is often 8 bytes, or even bigger structures like a structure or an array. So all those objects take different amounts of storage in your computer's memory, right? So here I'm showing, so most modern machines today are what we call byte addressable, which means every byte has an address. So you can individually access each byte, which is 8 bits. And a C pointer is just really an abstraction of that memory address. It's a way of hiding the details about memory addresses of a machine, but that's really what it is. The actual value that's stored in the machine is just a bunch of bits that are interpreted as a byte address by the hardware. And we'll talk about that later. But when you're writing this code and telling the compiler, this is a pointer to an int, you're giving the compiler the information it knows of how many bytes should I be fetching from memory when I access an int, or how big is it? When I'm accessing through this pointer, how many bytes should I pull in? So you tell it it's a pointer to an int, you're telling it to go get 4 bytes, for example. So here's showing a memory layout. We have just the byte addresses running this way. And so if I point it to an integer, it's actually pointing at 4 consecutive bytes in memory. So a 32-bit integer would be stored in 4 bytes. Another data type in C is a short, which is often a 16-bit data type. It's at least 16 bits. And that's stored in 2 bytes. And it's a character. The character is just a single 8-bit character, right? So depending on the type of the pointer, the amount of stuff that's accessed when you dereference the pointer will vary, right? Depending on the size of the object you're accessing. Question? Sorry, repeat the question. Couldn't hear. Void. Okay, that's a good question. So how big, what does a void pointer point to? How much do you access when you dereference a void pointer? Well, the correct answer is you shouldn't ever dereference a void pointer directly, because you kind of need to know the type. And so when you have a void star, it usually depends on the context. What do I assign to? If I say int x equals dereference of a void star pointer, the compiler will go, oh, you're writing to an int. I'll go get enough to fill up the int. And that's how it knows, by how you use the void star. Or you can explicitly say, this void star pointer, I'm going to tell the compiler, actually, that's a char star pointer. Just give me a character, by adding what's called a cast. And you say, treat that void star as if it was a char star. Question?
All the bytes right next to each other in memory, because I'm seeing those gaps, and it might be hard to find gaps in actual memory.
So the question is, there's are all these bytes next to each other? Why are these gaps here? I just drew it this way. There may be some other variable, maybe another integer stored here, another integer stored there. I'm just not using them right now. Next time we'll talk a lot more about how memory is actually laid out in a C program and all the different kinds of memory usage. But for now, this was just an example where I just showed this. I could have showed this pointing to here, but I just chose to show it pointing over there. Any other questions? Yep.
It's probably going to be a really stupid question, but I don't know, for whatever reason, this
Never a stupid question.
so why is it like 32-bit integers broken up into 4, 6, and 8-bit? Like, why couldn't you have some other? I don't understand why.
So a good question. The question is, why do you break up the 32-bit into 8-bit chunks? So this is something that architects over the ages have made different decisions about. Like, how big is the simplest unit? Like, why is it 8-bit bytes? Right? Why isn't it like 1 bit? Why doesn't every bit have an address? Or why doesn't every kilobit, 1,000 bits have an address? Why does every byte need an address? Byte is just convenient, basically because a byte holds a character in a Western alphabet, and so that was the original motivation for making it an 8-bit byte. It's enough to hold all the character set you need for Western languages. Later, as people evolved, there's a lot of other languages in the world, and we need more than 256 characters, so there's a standard for Unicode, which is a wider thing for a single character. But at the time it was developed, an 8-bit byte came about because it was enough to hold Western language set plus control characters plus some space left over. And then the other ones naturally are just, I need to, bigger units for bigger size words. But the primitive size is 8-bit byte. I think I mentioned somewhere here, yeah. So in C, there's actually this operator called sizeof. If you wonder, well, how big is an int on my machine? Sizeof is a built-in part of C, and the argument to sizeof is a type. So you can say size of int, and that returns a value, which is the number of bytes that object takes in the memory of my current machine, right? As I said up here, in olden times, computers had bytes that were 5 bits, 6 bits, 7 bits, 9 bits. So 5 bits was actually enough to encode an uppercase alphabet plus a few characters. So a lot of machines actually had character strings that were just represented as 5-bit bytes. And they were called bytes. 6-bit were common because a lot of machines had 36-bit words broken up into 6-bit bytes. 7 was pretty popular. The ASCII standard is actually a 7-bit standard. 9 was also popular because it also divided funky machine words up into units of 9 bits. The real reason we have 8-bit bytes, does anybody know? The power of 2? No. That's far too rational an answer. Now notice these were all very common. 6 and 7 were very common byte sizes before we settled on 8. Anybody know why we have 8-bit bytes? It's not because it's a power of 2. That would just be too easy. Yep. Say again? Well, the real answer is IBM. So IBM introduced a very popular line of machines in 1964 called the IBM 360 series, which they still sell. Their mainframes are based on that design. And it had 8-bit bytes. And they chose 8-bit bytes for a number of reasons, including they wanted to have 7-bit ASCII included, plus IBM had their own character set that they had to also include. And they wanted 8 bits, so they did 8 bits. And they were such a popular machine that the rest of industry followed. They had to be sort of IBM compatible. So IBM is why we have 8-bit bytes. Before, there's nothing to do with power 2. Right? It's just, thankfully, it is a power 2. It makes our lives a lot easier. But it wasn't for that reason that we have 8-bit bytes. Okay, so sizeof tells you how many bytes there are in an object in C. And we'll use this a lot more when we talk about dynamic memory management next time. Because when you want to allocate space for an object, you kind of need to know how big it is when you ask the memory allocator to give you that space. So C has explicit memory management. We'll talk about that next time. However, it's also useful to understand how pointer arithmetic works, which is something we'll talk about right now. So pointer, remember, is just an abstraction of a machine address. Right? It's just a number that we interpret as the address of a location in memory. But so we can add numbers to it. So we can add 1 to it. Now this is an example piece of code. This terrible code. You should never write code like this example. I'll explain why in a minute. But here's a few variables I declare. I say P equals the address of char star P. P equals the address of A. Then I can bump the value of P. I can increment the value in the pointer. So what do you think that does when I add 1 to P? What does it point at now? So it was pointing at A. And now I add 1 to it. What does it point at now? It points to the next byte. That's the correct answer. What's in the next byte? The correct answer is we don't know. That's why this is such a bad slide. But what it might point to is B, right? So I point, P equals A. And if the compiler had laid out the variables in memory such that A was in 1 byte and B was in the next byte, if I took the address of A and put it in P, then incremented P by 1, it would point to B, right? That's what I'm saying. This is awful code. On this side, similar thing, but notice the type here is int. Ints are bigger than chars, right? And so, usually bigger than chars. But I also did P equals plus equals 1. So this is a little odd, right? You might think, well, I should really add to P a bigger number to represent the number of bytes in an integer. However, the way the pointer arithmetic is defined in C is that the integers you add to a pointer correspond to units of the size of the object the pointer points to, right? So you have a pointer to an int saying P plus 1 moves you to the next int, right? So the units are units of integers. So C kind of keeps track of the type of the pointer, and based on the type of the pointer, any integers you add and subtract are in units of the size of the object it points to, right? So if an integer is 4 bytes, P plus equals 1 will actually change the address by a value of 4 to point to the next object. Now again, this is terrible code, and the C standard specifically prohibits you relying on this actually pointing to B after you've done this, right? The important thing to get out of this is that the increment to P is in units of the thing P points to in terms of how many bytes it is, right? So is that a question? Right, that's a great question. The question is, what if I had a byte next to an int, and the P pointed to the byte, I incremented by 1, now it points to the int. The compiler will let you do that. The problem will be when you dereference that pointer, if the type of the pointer is still pointed to byte, you only get 1 byte out of the integer. You won't get the whole integer, right? So that will be, unless you're meaning to do that, that'll be a weird result, right? Normally the way you use pointer arithmetic is working within arrays. So you have arrays of homogeneous objects, like an array of integers. And then you can use P plus equals 1 to step through the array. So we'll look at some examples of that. So one example we already sort of talked about was A subscript I is actually the same as, remember, the array name can be treated as a pointer. So take that pointer, add an index to it, an offset to it, and that actually will move the pointer by I times the size in bytes of each of the elements. So the underlying pointer number will change by that amount. And now it will point effectively to the ith element in that array, and then I can dereference it, right? So these are actually equivalent expressions, right? So the value at AI, or take the array name A as a pointer, add I to it, then dereference it. These are the same meaning in C. Right? So this is where arrays and pointers have this strange duality. You can move between one or the other very easily. Now you can move between the two very easily, but usually to make your code understandable, you pick one and stick with it so people understand what you're doing. Okay? And playing with pointer arithmetic, it's actually one of the cute things in C. There's a lot of cute, highly tuned code that's impossible to read using pointer arithmetic. So you can use it. It often makes your code hard to debug for other people. So here's passing arrays. When you pass an array like this, all you're really doing is passing the pointer at the base of the array, right? So when I pass an array to a function, like this, all I'm really doing is passing the value of that name, which is the pointer, to the base of the array. I have to separately pass the size if I'm interested in the size inside this function, right? So if I allocate 2 arrays here, in A10, in B5, this function foo doesn't know, if I didn't pass this 10 in, it wouldn't know how big A was, because by default, all A encodes is the start of the array, nothing else about the array. I have to separately tell the function how big the array is. Okay, so here's a little example. Here's a little test. So what does this print? If I take size of array, where array is the array name, what is that going to print? What is size of the array name? Yep. 4. You said 4 because 4 bytes for an int. Is array an int? So 4 is a pointer to an int, right? So it might be 4 if pointers were 4 bytes long. So size of array will print the size of a pointer. The pointer, that's the pointer to the array, right? Whereas in this context, notice size of A is now referring to this array here. And this has the right types. This will actually print 40 because it knows this is an array of 10 elements. That's the type of A there. The compiler can see that. When I pass it as an argument, I'm just going to see the value of A. If I just pass A, right? I'm just going to see the pointer to the base of A. Oops. Okay, so different ways of stepping through arrays. If I have an array here, I can do it this way explicitly using the square brackets and indexing. Kind of makes it clear I'm treating this as a sort of mathematical vector. Or I can initialize a pointer to the start of the array and loop until I'm less than the address of the end, and then increment the pointer this way, right? So there's a different way of stepping through the array, right? Which one's clearer? Which one's faster? That's a trick question. You don't know. It depends on the compiler. The old days, this would tend to be faster, but recently compilers can figure out they're actually the same thing. You get the same code out of both of them. But this is one of the reasons it used to be faster, because we had simpler compilers to do stuff like this. But now as compilers have got better, we don't really need these tricks as much. Okay, another clicker time. All right. So let me just walk you through this example. You have an array, a pointer to a pointer, couple of operations, then a print. So this is pretty simple, just a few lines of code. Should be trivial. Yeah, one thing about this code, it kind of looks like what we call line noise. You know, like in the old days, your modem had noise on the line and it looked like this. All right, let me start it off. Okay. What is PP? Well, PP is a pointer to a pointer. That's 2 stars, right? Because this example is easier, I'll just run it for 90 seconds. Okay, let's stop there. So, if I would take a look how people are thinking. C and D are popular choices. Running a little low on time, so I'm just going to go through this example. So, X is an array, 5 elements. P is a pointer to an int, and it's assigned to the base of X. So P initially points to the start of X. PP is a pointer to a pointer, and it points to P, right? PP, obviously it's a pointer to P. You take the address of P here, initialize it here. So this statement, what does this do? Star PP is dereferencing PP points to P. So this points to P and then increments it. So P, which originally was here, moves along one. Okay? This expression, star PP, well, that's pointing to P. So P, dereference P. Oh, that must be dereferencing the element that P points to. And then increment that. So this 4 now changes to a 5. And when I print it out, that's what I get, 5. So the answer was D. Okay? That was clear, right? Sit and work through this. This will help you understand pointers. Okay, in the news. So, writing code in C, as you see, is very bug prone. And this is one of the reasons why there are so many hacks and security leaks in the world today. One thing I thought was fun was Google exposing Apple security bugs. And they published these 90 days after notifying Apple. But Apple didn't quite have time to fix them, though. I think they fixed them today. One of them is, something to do with the network stack. Another one is dereferencing a null pointer. That's what caused the bug. Another one is zeroing the wrong part of memory. Another kind of bug, right? So these kinds of bugs we've been talking about today, they affect the big guys, serious systems. What I thought was actually quite funny was that separately, I think it was today, Google announced that one patch a vulnerability they have in WebKit, which affects everybody using Android 4.3 or earlier, which is about 930 million active users who have very easily hackable phones now running Android. Okay, we'll do the rest of this next time. But first, just in conclusion, give me a minute here. You got 2 minutes left. So important concepts. The array names and pointers have a duality in C, right? So an array name can be used as a pointer to the base of the array. And that's one of the things you'll see a lot in C. So array variables often are used like pointers. Array subscript 0 is the same as star AR, right? And array subscript 2 is the same as star AR plus 2. And get used to this idea of pointer arithmetic and the fact that the pointer, you need to know the pointer's type to do anything with a pointer, including incrementing it. Okay, we'll talk more next time.